If somebody offers you amazing opportunity but you are not sure you can do it, say yes. Then learn how to do it. Yes, I am talking about the amazing opportunity that knocked to our doors. That is DSA Carnival. With 17 speakers, 18 topics, and a global contest. Good evening, everyone. I am Sarika Purohit, first year IIST college student, and today I am feeling very privileged for getting an opportunity to be host of today's live session of DSA Carnival. So, today's DSA Carnival session and the topic going to be covered are divide and conquer, greedy and sortings. And there will be a quiz after the session and the link will be posted in the chat box. Quiz will be at Prep Bytes platform. The question of quiz are based on the topics that will be covered in today's session and it will help you to make grip on the topic. And now, for today our instructor is one and only Saptarshi Mukherjee sir. Sir is Master in Code Forces, a great personality from ICPC 19 regionalist. Sir is educator at an academy. Now, as we all are excited for the session, without taking much time, I would like to invite Saptarshi sir. Please, sir.
Yeah, hi. Can you all hear me? Please confirm. You all can hear me, right? I'd like to hear from some students maybe. Am I updated? Yes, I think so. Okay, great. So yeah, thanks for the introduction. I'm Saptarshi. I've graduated from IIT Bhilai. Maybe, yeah, just a second. I've graduated from IIT Bhilai and there I've pursued BTech. It has been 1 month since my graduation. And in this course of 4 years, computer programming is one of the things that I've done. Um, by the way, also apologies from my end that you all had to wait. In the last half an hour, probably there was some lag in communications. But anyway, okay. So let's start without any delay. So we have 3 topics, and most of you might have heard the topics. Now let me look at the chat because you all have sent me the answers. Many of you are beginners. Some of you, okay, you have been quite honest. Complete beginners, noob, nice, and some of you are intermediates. That's nice. So we can have more or less all parts of the topics. So we will see first of all how to begin in this sorting. What are the different ways in which we can understand when to apply this sorting, why at all sorting is important, and then finally we will step into the place where we can see on top of the basic stuff that we ordinarily use in sorting, what are the more interesting facets that exist in this field. So when you're in intermediate category, I assume that you know the basic concepts. So the only thing that you can take from these sessions, or one of the things that you can take from these sessions, is how we'll be comparing, how critically we'll be analyzing them, and finally some of the problems that we'll be solving. So that's it. I'll be certain. Okay, I've seen you all in the previous sessions. I've seen some glimpses in your last 2 sessions to get an idea of the kind of audience you are, and it will be nice interacting with you. One thing that I must bring to your notice is I will be on my own pace. I would take up the topics. I'll be switching between them. If you feel confused anywhere, just do feel free to just write down what your problem is. From there, I'll be able to take the adaptive steps. I'll be able to adapt my steps. Fine. So let us now start. Are we also going to code? That will depend, because the primary thing is the approach, and if you get the approach, then the coding you can do for the rest of the year. You don't really need somebody like me. So once the approach gets implanted in your minds, it gets ingrained, you don't require anybody. But one thing that I'll be stressing on is how we can grasp the topics in the best way we can. So we will look through certain examples, certain insights, and fine, that's it. There are 3 topics, and we'll be trying to distribute the session between the 3 topics. The total session shall probably reach 2 hours. It will range between 1 hour 30 minutes to 2 hours, and we will start from sorting. After having spent some 35 to 40 minutes in sorting, we will enter into divide and conquer, and we will have sort of divide and conquer and sorting together. We will see how they are implemented together in certain applications, and then we will proceed directly into greedy algorithms. Now, while uh, you all are interested, and it's nice to see all of you, waiting and gazing for an interesting session, the important thing for you all to take away from here is the crux behind each of these topics and how you can extend them for your problem solving, because these 2 hours are not going to be the end of these topics. There is going to be a lot of things to be done beyond this. Somewhere I can be a part of your journey, somewhere I won't be a part, somebody else can be a part, but what is important is you keep practicing so that you gain more and more insights, because the deeper you go, the more interest you gain. I will try to you know throw some light on those interesting facets, but okay, let's see. So I'll be sharing the screen. DSA Carnival. Fine. Is used with 2 monitors. Let me know, can you see the screen? It should be visible. Yeah, it is. Fine. Sorting from beginner level. Okay. So, fine. I'll keep that in mind. Let's see. I'll start from a problem. You all will analyze the problem. Don't think about sorting. Don't think about 100 things. Let us see what are the things we can do. So the problem goes something like this. Consider that there is a restaurant. I'll not write the entire statements. There is a restaurant and it is being visited by n people. Okay, the sentence got completed. It is being visited by n people, and they have their own arrival times, unique arrival times. So basically, I'm representing n people by the arrival times. They are all arriving at certain timings. One is arriving at suppose 1 o'clock, another is arriving at 4 o'clock, and we have them as integers. So we have suppose some timestamp. Yeah. आप क्या पढ़ा रहे? Okay. So yes, we are starting with sorting, if it was not clear, and we are starting with a problem. While you're seeing the problem, you can forget sorting and thousands of other things. Just focus on the problem. So a restaurant is being visited by n people. There are unique arrival times, and we need to find the minimum difference between arrival times of two different people. I'm sorry, two different people, two different persons. So what I mean by this is, suppose we have been given the arrival times in this manner, 1, 5, 11, 7, 4. Okay. Suppose these are the arrival times. They arrive at these times. So these are integers. Please use Hindi language if possible, definitely. So I think we have combined audiences. So हम क्या बता रहे हैं? I'll use both the languages. I'll keep on switching. Let me know. Thanks, someone, for pointing it out. So हम क्या कर रहे हैं? We have these arrival times. मतलब ये लोग इन times पे आ रहे हैं. ये वो वक्त है जब ये लोग आ रहे हैं. And we want to find out what is the minimum difference between the arrival times of two different people. So when we consider the first two people, पहले दोनों को अगर हम देखें तो एक टाइम 1 को आ रहा है, दूसरा टाइम 5 को आ रहा है. What is the difference? The difference is 4. It is 5 minus 1, that is 4. This is for the pair 0, 1. Fine. 0, if we look at it, in zero indexed format, this is what exactly we get. If we look at some other way, suppose we have 0 3, then exactly what is our, like, what is the difference in the arrival time? 7 minus 1, that is 6. Please let sir teach and don't disturb. Okay, I don't know. No, you can keep on writing, like, but anyway, if something, some important chat gets lost, then let me know. You can bring that into attention. So what we are saying is that for any ij where I and j are positions and I is not equal to j, what we can do, this is the brute force thing, what we can do is, for this there exists a difference, that ith person has arrived at this time, jth person has arrived at this time. We just need to do the absolute value of the time, arrival time of I minus the arrival time of j, right? So this is basically what we need to do. All the arrival times are there, we know how many pairs are there, that is exactly nc2. So nc2 pairs are there, which is, we can say, you have done the time complexity lessons and all, we can say that is n square. So we can say out of these n square possibilities, we can go on finding, we can go on searching for where we get the minimum value of this particular thing, and the moment we get, we are done. So this is one approach where we know none of these possibilities will get skipped out. Let me know if this is n square brute force approach would maintain a variable and run the nested loop, right? So all that we'll be doing is, what we are doing here is we are considering all pairs. We are considering all pairs. If we look into the implementation, something that Sid has mentioned, it will be something like this, that we will consider all the possible i's. So I will be something like, we'll proceed from I to 0 to n, and suppose that I has been declared before. So I had seen somebody's message that, by the way, my camera is not visible, I think, together. But anyway, I had seen somebody's message. He wanted me to code in Python. So if you don't understand any line, then let me know, because the focus is not on the syntax. It is basically on the approach. I can code in C++, Java, Python, whichever language you want. But the important thing is the algorithm that I'm using. I'll try to be I'll try to use such codes which are generically used in all the languages. So you have this j equal to 0, j less than sorry, we'll look for all the other, complements. So if I is the first person, suppose we choose some person over here, and we want to see that, okay, for any person who can be the left one that is in this list who occurs in the left, we can choose what is the right one. Why we are doing this? Because, okay, I'll tell you that. First, we can do something like this, that from the next person, we have chosen the ith person. Now from the next person, which is I plus 1, we can travel up to the end of the list, and we can say that we will update our min based on this. Min equals to minimum of, or suppose this is min 1, this is min 1, comma, the arrival time, that is absolute value of basically the formula that I wrote above, the difference between the arrival times. Explain if you solve that. Yeah. So this is basically, I'm telling you, this is the brute force approach. You might ask, why are we starting from later? So suppose my final pair, that is something like 1 3. Over here, what is the pair? What is the pair that is going to win? You know that the difference like is the least for 5 and 4. So in this case, the pair 1 4 is going to win. So you can say that, okay, 1 4 and 4 1, they are almost equivalent, like they are equivalent. I don't care about in which order I consider the pair. It is an unordered pair for me. So that is the reason we are saying that, okay, we will just first focus on the left element, which is I, and then we will explore what element can be the next one. And as many of you have pointed out, that we will sort the array. The important thing is, which I always want anybody to explore before rushing for the solution, why are we sorting? Fine, why are we thinking of sorting? Now you can understand that what are we doing over here? We are considering all the pairs 0 1 0 2 0 3. I hope you all can understand what is this 0 1. Snehashish, is this brute force approach clear to you? So for any ij, we are considering that pair, and we are updating our minimum variable. You can let me know if you are confused anywhere. This is basically telling, so over here we are considering a particular ij, and using those two for loops, I have just iterated over all the possibilities of those pairs. That is how we are getting the minimum value. Fine. So now I would okay. So now the important thing is that for this 5, we know that the answer is 4. Are the people who have come before 4 really important to us? Like this particular value 1, is he really important to us? We know that before me, just before me, some person had come. Before him, who had come? Is the difference of time between me and those persons really important? That will always be greater, right? Yes, Gotham, I understand. I less than n minus 1 is definitely the right way. And I was about to write that. But the reason I did not write that is just to keep it simple. So even in your bubble sort and many other things, we often, use this optimization, but that doesn't change the total time complexity. Anup Kumbhar was talking, yeah, please don't, learn na mat chalu kar do. Let's stay adhere to the topic. काफी कुछ है, we want to cover as much as possible, so let's be harmonious. What we are telling is that suppose this is the timeline, and a person comes here at the time 4. Another person has come at 5, another person comes at 7, another person comes at 11. For this 4, this 5 is a person with whom we are seeing what the time is. हम इसके पास देखेंगे, हम देखेंगे कि इसमें डिफरेंस है 1. वी विल ट्राई टू सी कि 1 के कम में कोई डिफरेंस है कि नहीं, यहाँ पे कोई एलिमेंट प्रेजेंट है कि नहीं, यहाँ पे कोई एलिमेंट प्रेजेंट है कि नहीं, whether there is an element present in this zone or not. But will it really matter? Like, if we don't consider these elements, will it really matter? In other words, will these elements ever be important for this element 4? Once that we have found 5, is the participation of elements 7 and 11 really important? What is your intuition? Because I need the minimum arrival time. So this is the minimum arrival time. Once I found the one who is coming after me, and I found the one who has come before me, do I need to see who has come after this guy and who has come before this guy? No. Okay, Gotham, min we are using, yes, we can use the inbuilt function, we can use anything. Min is just taking 2 parameters. It will take min1 and it will take the absolute value, and it will say that what is the minimum among them. That's it. Okay. So now we understand that this is not required. So this is where we gain the intuition that over all the possibilities which we were correctly analyzing using this for loop, all the possibilities are not important to us. For every person, what is important? The next person who is coming just to its right, and the immediately previous person who comes just to its left, right? So that is what we are trying to gain, that just for every person over here, what we are doing, for every I, we are checking up to n, I plus 1 to n. So if you look at I equal to 0, there are n people, sorry, n minus 1 people. If you look at I equal to 1, there are n minus 2 people, and so on. So that is the intuition we are gaining, that instead of n minus 1, n minus 2, and those so many people we were comparing with, we are reducing it directly to 2 people. Now every element needs to be compared to just 2 people, one who is on the left and one who is on the right. And that will give us the intuition, that will give us the sorting. That will give us the answer. The answer to what is the minimum arrival time. For every person, I will just look at who came before me and who came after me. But now the problem is, the thing that Prithvi has mentioned, that we will just check the adjacent indices or indices. The problem is that for 5, the person who comes just before him is not located adjacent to him, it is located far away from him. So somewhere this greedy choice of choosing the best 2 people, for choosing those 2 people, we have to explore the entire array to find out who those important people are. We have to perhaps run a loop to see who is the one just greater than me or who is the one just lesser than me, right? Now suppose if we could have done something that arrange it in the ascending order or in a sequential order, suppose we arrange it like this: 1, 4, 5, 7, 11. That is exactly how they appear on the number line. Sagar, is that for me? Anyway, so okay, uh, I don't know if there is a lag or not. Anyway, so and there you go. If you have this arranged order, what you gain is, now you can readily, once you have this arranged order, you can readily say that for 5 I need to care only about 7 and 4, which is, for I there are only two indices, I minus 1 and I plus 1. Okay, Sagar. So there are only two indices, and for every I we need to check only these two. But so are you gaining it? We just need a modified form of this array, a modified form in which I can see all the people in the increasing order of their arrival times. Once I get in this order, I don't need to search the entire array to see who is just greater than 5. I can say the person in front of me, he is greater than 5. That is myself. 5 will tell the person greater than, like the person just in front of him is the one who comes just after him. So we need a rearrangement based on one single value, and that is exactly what we are doing using sorting. Sorting basically tells us, sorting is basically rearrangement of elements based on certain function. So it can be, if the element is of one value, like a person has many characters, we are not concerned about the age of a person, height of a person, and so many things. We are concerned about the arrival time of a person. And later on, when you will study different complex stuffs like object oriented programming and other things, you will see that every element, every object, every substance in our, whatever we are considering, in the ecosystem we are in, every object is represented by the various parameters, by the different behavioral factors. Like when we talk of a person, we have the age, we have the height, weight, and everything, and there is this arrival time. And on the basis of what we will be categorizing things, that is basically the focus of our sorting function or whatever we'll be performing. So when you go to, suppose you go to a size of go to a site of Amazon. Suppose you go to a site of Amazon, or you go to a site of Flipkart. If you go to these sites, you can basically see, you will get certain options like sort by price. You enter a commodity, it will provide you the list of all commodity, then you provide sort by price. What it does is that it forgets, suppose it's a mobile phone, it doesn't take into consideration the camera details and all your processor details and battery specifications, nothing. It doesn't take into consideration anything. It forgets everything, and it says only on the basis of price it will sort the elements, that is rearrange the elements such that either it will be increasing in increasing order downwards, or it will be in decreasing order downwards. And from this simple example, you can understand how heavily it is used in our real world examples. For 0th and n-1th index, we need to handle the case separately or not, right? Yes, Rohan. Yes. So we need to handle the example separately. What Rohan has said is that everywhere we are checking the left and right. So what about the first person? How can you check to its left? To its left, nobody is there. So if nobody is there, just don't check it. So we will form this rearranged array. We will form how they stand in the line, and then for the first person we will say that first just check the next element and leave. From the second element till the penultimate element, that is the second last element, we will check for every element the left one and the right one, and for the last element we'll just check the left one. So now if we consider how many total comparisons are we making, how many total subtractions are we doing, one for the first element, one for the last element, and one like two for every other element. So it is 2 plus, or if we write one by one, it is 1 plus 2 into n minus 2 plus 1. So it comes to 2 into n minus 1. That is basically the number of comparisons which you might have known. This is order n. So if we somehow get the rearranged order, we can solve the rest of the problem in order n. And this is basically the purpose of sorting. So while we sort, we treat this sorting like a black box kind of a thing, that there is something which will sort this function for us. We will pour an array which can be anything. The array can be sorted beforehand, may not be sorted beforehand, may be very badly sorted beforehand, I mean very badly unsorted beforehand. It may have slight deviation from sorting, whatever it will give us a sorted array, and we can say now whatever we get over here, that is a sorted array. And when we have this sorted array, we can solve the rest of the problem in order n time, and this will give us the result. So if we hadn't used sorting, we would have taken order n square. And you might have understood that the total time complexity now is dependent on two different components. One is this brother that we are seeing in between, which is going to sort this, and another is this operation which is going to take order n time. So that is basically the summation of both the time complexities, or basically taking the asymptotic maximum counterpart out of them, or maximum component out of them, we can actually frame them. So if your sorting takes order n square, then we are back to square one. If it takes order n square, then we can say that it will eventually lead to order n square only. However, if we can improve this to small o of order n square, small o means which is asymptotically always lesser, strictly lesser than n square. We use small o in that case. So if it is always lesser than n square, then we can confirm that using both, we can actually form a small o n square algorithm of finding the minimum waiting time between two people. Fine. So now that we have sorted, you know what we have to do. And now the important thing is, how can we sort? What are the important things that we need to see in sorting? Well, we will look at that, but just a short question. Suppose suppose instead of asking the minimum arrival time, I just ask a different question, that suppose you need to find the maximum difference in the arrival time. What will be your approach? Should we use sorting? And if you use sorting, or if you don't use sorting, what is going to be the time complexity? Mention these two things. Will you use sorting? And if you don't use sorting, what will be the time complexity of your approach? Exactly. Prithvi, Prakhar, they have given the right answer. And okay, so the important thing is, in case of maximum difference, what do you need? Just the minimum arrival time and the maximum arrival time. If you find out by just one iteration over the entire loop that who is the person who has arrived at the very beginning and who is the person who have arrived at the very end, you just require one min function and one max function. You just iterate the entire array, you will get that. So when you just find out the difference, you get order n. So that is basically an instance, or basically a slightly changed problem where you don't require sorting. And this is something which I wanted you all to understand. Fine. So we can find, right? So that's it. That's basically about sorting. Whenever you sort, just try to think about whether sorting is really required or not. There are many places, and because we know that at many instances, sorting actually takes order n log n time. Many algorithms are present which take order n log n time, and this log n multiplicative factor does make really small difference. In many contests, you will see that order n and order n log n perform much equally. They don't matter which one you do. Like if n proceeds to something like 10 to the power 3, then it will get, this log n will be something like 10. So it will get multiplied by 10 times. And usually if your number of operations that goes up to 10 to the power 6, it can afford up to 100 operations more, like 100 operations times. It can afford up to 10 to the power 8 operations per second. So often people use sorting even when sorting is not really required, but it is always a good practice to understand where you require sorting. That is it. I will go through a few sorting techniques now, and so that we create the basis on the basis of which we'll enter divide and conquer, and we'll see how we are improving. So the first sorting technique that we'll be analyzing is selection sort. Now this is how selection sort works. When you have the previous array, are merge sort, insertion sort, bubble sort important in CP? Merge sort is important in the sense of divide and conquer, because divide and conquer forms the basis of many important problems. So merge sort becomes important. Insertion sort is one of such problems which comes intuitively. That is why it is being taught. Bubble sort, it is not really required, but if you ask me about interviews, uh, questions can be framed on them, and there are many interesting insights that we get from all of them. So ideally, yes, for interviews, for such purposes where you want to prepare yourself for the best sorting practices, you need to have a good insight about all the different sorting algorithms, or at least many of them. Not all, many of them. So in selection sort, we do something like this. Suppose we have this previous array. I don't remember. We had something like this. Okay, there's I think a storm brewing over here. I hope it won't create any interruption. 151174. 151174. What we are getting is, suppose that at every step, what selection sort tells us to do is, at every step, at every iteration I, choose the best element for ith position. So those who have already known selection sort, just recall the things. We are going to analyze it shortly, the important things. What it says is that at every iteration I choose the best element for ith position. So if you look over here in this example, what will we say? First, in the 0th iteration, we'll look at the 0th position, which is 1. So now at this position, at the 0th position, which is the best element? The shortest element in the array. If we are sorting in ascending order, we require to know what is the shortest element of the array. So what does it require to do? It has to run through the entire array and find out what is the best element. When it gets the best element, it will place that 1 over here. Now suppose the next step, when you're at the next step, you want to find the second best element. What it will do, it will again read through the positions 1 up to the end of the array, and it will find out which is the best element over here. It will add that element, that is 4. So basically it will just conduct a min operation which will run through order n time, and it will find out the best element and it will put it over there. Again, for this part, now how it will put it over there, it will basically swap these elements, what is present currently at position I and what is present, like and the position where the correct element is present. So this is 4 is the correct element that is present, and 5 is the position where we are interested to bring 4. So we will swap so that this element, which is the larger element, now gets into the position where our perfect element is present. We don't need so many swaps to bring 4. We are just concerned about throwing 5 away and bringing the correct element in 5's place. So what can you ensure that after the ith iteration, what actually we are ensuring is, first I elements, first I or I plus 1 elements, if you consider this zero indexed kind of thing. So this extends from, or we can simply use the so the elements, the array in the position 0 to I is sorted. And not only that, not only are they sorted, not only this subarray, the first part is sorted, but they have the perfect elements. What I mean by this is, after the ith iteration, the first I elements get their perfect candidates. Is this idea clear? Wherein how to find if it requires sorting or not, that is the simplest idea, that when you are at a position, do you really need to consider the calculation with all the members, or according to the order you can restrict the number of operations to only a few people. That is basically where sorting helps us in throwing away unnecessary computation. Okay, so whatever problems you solve on sorting, this is basically the philosophy. In that restaurant problem, we were identifying that for any person, we just need to compute with the person who comes just after him and the person who comes just before him. That's it. So over here, what I want you to understand is that after the ith iteration, the first I elements are sorted. So you can understand that after the last iteration, which is n minus 1th iteration, the entire array will be sorted. And how we are sorting it, basically this is how we'll be doing that. For I equals to 0, I is less than again n minus 1. Why n minus 1? Because by the time you sort the first n minus 1 elements, the nth element already gets sorted. So over here you will bring 4 over here, then the third element, when you will try to find the candidate, you will find 5 over here, 5 will go over there, you will explore through 11, 7 and 5. So before this iteration, you will have 1, 4, 11, 7, 5. How 5 came here? After swapping. Now we will say from here, the minimum element is 5. We'll place 5 over here. Then what will happen? These two will get swapped. Now 7 and 11 are in the correct place. It will check, it will place 7. When you place 7 over here, that is, all elements are completed except the last element. We know last element is already in its place. Last element has to be in its place. So if the first n minus 1 elements are sorted, then the last element is also sorted. That is why we can just do n minus 1 iterations. And then what can we say? That from the ith element till the last element, we just need to check what is the min. So here we can initialize something. We will now find out the min over here for this particular range. Again, the similar calculation. I'm not writing the entire thing. And over here, we will just say, coming outside, we can basically, for this min, we can actually store which is the appropriate k. K in the sense that whichever j is bringing us the min, we will store that as k. So k is the position where the minimum element has been found. What we will say now, just swap the positions I and k. You all know how to swap it. There are so many ways of swapping it. So you can just swap the positions of I and k and you are done. This is basically the algorithm. This is basically the algorithm of selection sort. So if you analyze the time complexity, what will you get? For the first element, you need to explore n minus 1 positions at maximum. Means definitely you need to explore n minus 1 positions. In fact, if this loop starts from I and goes up to n minus 1, then actually you take um, n positions. You need to check through all the n positions to find out which is the minimum. For the next element, you need to check n minus 1 positions. For the next element, you need n minus 2 positions. And for the, we know that we have to continue only up to the second last iteration. We don't need to go up to the last element. So the last one will be 2. We need to compare 2 elements and find out which is the minimum. You can find out that if we compare for the last element, you need to find out the minimum out of only one element, which does not make sense. So that is why we are saying we will do it for less than n minus 1. What is this calculation? N into n plus 1 by 2 minus 1. Yes. And can we say that there is n square? That's it. So this is how normal sorting techniques work. Now, I would encourage you, but before encouragements and philosophies, the important thing is to analyze it a bit critically. What are the things? What are the, first of all, it is having order n square, which is not really good if you think of our previous example. It is having total computation time as order n square. This is the total time. What is the total number of comparisons it is making? Total number of comparisons. Comparisons. Comparisons means this min variable is actually storing the min seen till now, and it is comparing itself with the element at the current position, at any ith position, at any jth position. So that is comparison. So this is actually, I'll change the color. This is actually where this comparison is taking place, where you're updating min. So here all this comparison takes place. So how many times do you think this runs? Exactly. So you will have order n square over here as well. If you say that, okay, for the first case, we were considering n because one value will be starting with and then n minus 1 will be comparing. Comparison stand only for n minus 1. We can do that. For the first one, there is only n minus 1 comparison. For the next one, n minus 2. For the next one, n minus 3. If you say that the element will be initializing with, that should not be counted as comparison, we can do this. And the last element will be 1. What will this end up to? Once again, the same thing. It will be n minus 1 into n by 2. It is n into n minus 1 by 2 minus 1. This is also order n square. Those final constants don't matter. So you can say number of comparisons is order n square. Now coming to the next important thing. What is the number of swaps? Total number of swaps. What is the total number of swaps? Yes, we can explain about stable and unstable sorting. I'll come to it. Okay, I'll do just after it. Yeah, thank you. There are exactly n swaps. So when you compare this with other algorithms which have order n square total time, you actually find that yes, n minus 1, right? So order n. So we are only worried about the asymptotic time complexity. You will find that when we compare with many other algorithms like bubble sort, this is not the case. Bubble sort uses order n square swaps. And why is this swap important? Because in your memory or in your hard disk, wherever it is stored, wherever it is being computed with, there is a kind of overhead involved in creating these swaps. You fetch the value from here and you place it over here. There are actually many transistors and other architectural elements which have to process this. So swapping is not a very efficient task. For comparing, you just need to fetch the value, and there is a simple comparator circuit which can do it. But if you consider the swaps, then it is not so easy a thing. So that is why we say that if we can optimize the swaps, then that is one aspect in which we prioritize or we favor one sorting algorithm. And yes, sorting algorithm which allow less swaps, we have selection sort. In case of insertion sort, I would encourage you, I won't cover it today. Insertion sort, I would encourage you to see for yourself. What we do is basically something like this. What you might have done when you might have sat on a deck of cards. So the way you actually rearrange the cards, suppose we reach this particular element, and up to here all are sorted in themselves, and you find that this element is smaller than two elements. You bring that over here and you say, I will take this over there and take this over there. That is simply what is insertion sort, nothing else. So over here, what can you say? Again, the swaps are quite large. Now if you say that, okay, they are just going to the next position and we can optimize it better, then you are depending on the architectural uh, aspects. But if we just count the number of change in positions of elements, then it is again order n square. This is how. And in case of bubble sort, it is slightly different. Again, I would encourage you, but bubble sort, there is an important thing whenever you study it. There is one thing. Suppose an array is already sorted and you get this. Suppose an array is already sorted and you run this. How much time will it take? If that is already sorted, how much time will it take? Will it still take order n square? Will it take less than order n square? Will it take order n? Something different? What do you think? If it is already sorted. Okay, let me then throw light on this. See, here we are not checking at any part, we are not checking if it is already sorted or not. It is not sorted yet. It is not sorted. You're like, we are not checking if it is sorted or not. Even if it is sorted, we are telling that, okay, read through the entire array and do this. This is the basic implementation. What I've written over here, this is actually the implementation of selection sort. We don't check in between if the array is already sorted. So it will proceed till the end. Every iteration, it will process for every I. It won't break in between. For every I, it will check. For all the j, which is the minimum element, it will see that, okay, minimum element is already at its place. It will not swap. So you can see this particular operation may be omitted, but this operation will always happen. And when this operation happens, you cannot improve the time complexity. So selection sort is order n square even in case of the totally sorted case. And when you study bubble sort, differentiate between them. In bubble sort, you can easily identify whether you can stop the sorting midway or not, but here you can't do that. Cool. Asymptotic notation is way to measure algorithm without running on actual machine. Yes, but didn't you all cover it in the first session we had 2 days back? Anyway, that's not an issue. You can go back and see. Yeah. uh, yeah. Now the important thing, can we improve it? So I've already unfurled to you bubble sort and those things. We cannot do better. Bubble sort, insertion sort, the total time complexity is always order n square in both, especially in unsorted array cases. Bubble sort also can't do better than order n square. Can we do better? Now we will look at a very different paradigm, and we will be entering divide and conquer. Can you say about inversions? Yes. So inversions, okay. um, Inversions is more involved in bubble sort, and it gets involved in many different problems. Like in divide and conquer also, we can see on one problem. So insertion sort, since you have mentioned, let me mention over here. Insertion pair, you asked about inversions. Okay, so inversion pair is a pair ij such that I is less than j and ARR I is greater than ARR j. Does this make sense? Inversion pair is a pair of indices I and j such that in the sorted order, what should have been the order between ARR I and ARR j, it is just exactly in the opposite order. That is what is inversion pair. So that is basically inversions. Now the number of inversions is the number of such pairs which exist. So if you look at that example which we were dealing with, one what was that, 1 11 7 1 5 11 7 4. So 1 5 11 7 4, we can say that with 1 there is no inversion, they are always in the correct order. If we look at 5 and 4, there is an inversion. Why? 5 is located before, but 5 is greater than this. So I equals to, we can actually represent it like this. In zero indexed case, indices I4, sorry, 1 4 represents an inversion. Why? Because ARR I is greater than ARR j. Similarly, we can say that 11 4, we can this again is in the opposite order. So we can say that 2 comma 4 is an inversion. Similarly, 5 comma 7 we have, 5 comma 4 we have, 11 7, 11 4, 11 7 we have 2 3, and 7 4 we have 3 4. 2 4 3 4, I think we have done, right? Yes, right. So since some of you know Merced, I think now we'll be entering some place where you all will find some interest. This had to be the beginning. So that's about inversion pairs. Anything that you have got to ask, anything else you have got to ask in selection sort, in the basic sorting we have discussed till now? Almost half an hour is about to conclude. Sorry, 1 hour is about to be concluded. We'll proceed into divide and conquer now. Anything that you have got to ask before we proceed? Okay, so let's proceed. Just a second. Okay, so now the important part is how can we optimize it? Some insights on sorting required for placements. Some part of it you can get in the greedy part that we'll be discussing. So in greedy, what we do is we try to find out the locally optimum solutions. See here, what we are interested in finding in the restaurants problem, we were interested in finding the globally optimal solutions. That is between any I and any j, what is the best. But what we said is locally, if we just analyze for any person, just locally analyze what is the best he can do, what is the best he can see around himself. And if we take the mean over all the local things, these are local measurements, then we will get the global optimum. These two terms, if you remember, and if you correctly implement, then in placements, I don't think there is any more intricacy in case of sorting. For better, in terms of insight, this is the only thing. And in greedy, if we get some time, we will analyze some really good things, how to prove greedy algorithms, how to analyze greedy algorithms, and we will have many facets from sorting as well. So yeah, some insights on sorting required for okay, when greedy fails. When greedy fails, there are many cases. We know, like traveling salesman problem. We never know, right? That from a particular point, if we start, we have to cover the entire route. We have to kind of cover all the cities, and every time if we pick up the greedy path, whichever is a greedy edge in front of us, that won't work, right? A simple example is this. Um, we have this, we have this, we have this, and from here suppose over here we have 1, over here we have 100. These are edges. These are edge weights. But over here you have 10 to the power 5, and from here you can go here in just 2, you can come here in just 2, you can come here in just 2, and from here also you can come back in 3, in 2. So suppose you don't choose this 100, if you like, this is a starting point and you have to come back to this point. So what will you do? The best is you pick up 100, you pick up 2 after that from here to here, then you take this 2 and then you take these 2, and then what will happen? This is your total cost. So this is the best cost by which you can travel in this cycle. Now you will say that okay, we need the best cost, so let us optimize locally. So what can you pick up? I will optimize locally. So most greedily you have picked up that I have optimized my approach by 100 times. You say I have optimized my approach by 100 times. So you have picked up 1 and you say I'm going to win. I'm going to have the least value. And then you face this and you have nowhere else to go. You cannot go back. Like you cannot visit the same point twice except that single point. And it doesn't make sense. From here again you will follow the greedy approach. So you will follow this 10 to the power 5, then you will follow this 3 and then 2. So 10 to the power 5 plus 6 is basically the cost that you pay for adhering to the greedy algorithm. 0 1 knapsack, definitely that is another such problem. Sorting with STL method. Yes, so before proceeding to divide and conquer, I think I should mention this. If you sort in C++, then definitely you just need to include the usual things, bits slash stds C++ and those things, and then you can just call this. If it is a vector, you can write vector dot begin. This is not a semicolon, this is a comma, v dot end. This is basically to sort in a ascending order. If you have to sort in descending order, you can write v dot begin, v dot end, and then the comparator. Comparator tells how you will be sorting it. So you can mention here uh, greater int. Here you have to mention the data type. So what it does is it usually it compares how it will, how ARI is less than ARJ. So you are telling that whenever it will be like ARI less than ARJ, this says that I will come before J. This is how it does it internally. So if you say greater is going to be my function, then you just do the opposite task. Instead of this, you just check if it is greater than. Then you will get just the opposite thing. If this holds, you will get J followed by I. And this will hold for all the pairs. Right. And if you want, you can even do some operator overloading. I think I'll have some programs that I can show you. Okay, it's open. You have, let me see. Okay, nice. So now see what I'm doing over here is there is some time based on which I want to sort these elements. I hope you all can see the screen. What we're doing is we have a set of vectors where every element is basically a pair. Every element is a pair, not pair in terms of the pair thing that is defined in your C++, but I have defined a separate class for this. And using this class, what we are doing is we are using these parameters, we are defining every object of this class. And now while sorting it, how I'll be doing is if the starting times match, then sort by the ending time, else sort by the starting time. So what I'm doing when I'm doing this sorting vector.begin comma vector.end, here I'm telling it how it has to treat this operator less than. I showed you less than in the on that page, right? So less than is has been defined over here, that how less than will be behaving. This is how less than will be behaving. So when you say a person less than another person, it doesn't make sense. But when you define that a person is less than another person, if this and this hold, this condition holds, if his height is less than that person, or if the heights are same and the weight is less than that person, if these things hold, then you say that okay, then it is considered to be less than. When you do this, you just have to pass a sorting function. So from this vec only it will understand, since vec is an object of type, like it contains elements of which are objects of type time. Time is basically a data type, a class which itself is a data type, non-primitive. So it is being trained on how it has to consider, how it has to analyze the less than and greater than operations. R dot begin r yeah dot r begin r end also suffices. You're right, and there are many messages. Shortest path in multi-stage graph where greedy fails. Multi-stage graph. Anyway, it's good not to digress so much. I think. So instead of like this is called operator overloading, where we are defining how this operator is going to behave for this particular class. You can also have some other ways, like you have over here. Here I've defined a separate function object by the name of custom. What I say is, you remember we used to pass a comparator over here, which is greater int. Now I'm saying that don't use something greater int which the library knows. I'm using something that I am dictating. This is what will be done. So custom is something that I define as a struct, and I add that later on. This is how these objects will be sorted. And definitely when you learn all of these things, when you become expert in all these things, there is another one that you can always explore and use, which is lambda functions. In case of lambda functions, directly from here you can pass that what is the way in which you'll be sorting. You can directly pass over here, so you can study about that. Those are advanced things. In case of Python and Java also, it works in the same manner. In Java, since some of you might be Java coders, Please take care if you use arrays.sort ARR. This has a worst case time complexity of order n square. So please be a bit cautious. Only when ARR is primitive. Primitive data type. If it is non-primitive data type, that was perhaps developed or added to the library later on. If it is non-primitive, then it is optimized. It follows n log n. But here it actually follows a dual pivot quick sort. Quick sort, I don't think we can see in great detail today. We can discuss on some other session somewhere else. It does not have, no, it does not have, but you can find that in many code forces contests where you have 12 hours hacking. There are many people who sit and figure out the cases for which this order n square will come. And I have been a victim of one such incident when my code failed the test case just because I had used this arrays.sort. So nobody will perhaps know it better than me. It uses dual pivot quicksort. So what happens to dual pivot quicksort? If you have the idea, Dhruvil, okay, Rohan, just a minute on this. Dual pivot quicksort. In quicksort, it is very common that the worst case time complexity is always order n square. In dual pivot quicksort, two pivots are always seen, but there also, depending on those two elements, and if you frame your elements in that manner, you can always end up at order n square. That is what happens over here. But in C++, if you ask, C++ uses something called intro sort. So this is basically, it is always good to know when you apply something in certain interviews, you directly apply the sort function. You should know a bit. It uses intro sort, and over there, for very small lists, it actually uses insertion sort. But the main thing that it always uses is quick sort. But if quick sort fails to perform good, when it understands in order n log n time that quick sort is not really doing good, it automatically shifts to heap sort. Yeah. Okay, so there you go. We'll not be covering in a greater detail these things, but I would encourage you all to look at it. Let me see. Any questions? Uh, hmm. Divide and conquer, DNC. Now, let us look at it. Suppose this is your array, and I tell you that you break it into two parts, and somehow you break it into two parts, and somehow you get the solution to both of these. Somehow they give you the solution. Complexity of C++ always n log n. C++ sort always n log n, but if you follow Q sort and certain other things, then you can face n square again. In Python also, be cautious. There are many variants. But in Java and Python, the thing that I mentioned where problems arise, or yeah, in this case problem arises, but anyway, there are some optimized aspects of team sort, which basically comes into the picture when the non-primitive data types are dealt with. So you can study about them. So complexity of collections.sort is order n log n. Yes. Oh, I'm sorry, I forgot to mention it. You should use collections.sort always. If you are in Java and you're taking part in competitive programming, you can safely use collections.sort. It is always order n log n. Cool. Good. Now let's come over here. Divide and conquer. Forget about divide and conquer and these things. Suppose you have two arrays which are sorted. Suppose this is sorted and this is also sorted, but mutually there is no relation. It can happen that all these elements are smaller than these. It can happen the exact opposite, or anything can happen. Suppose this sorted array is something like 1, 7, 15, 18, and here it is 2, 3, 6, 22, 24. To sort such two arrays, suppose both are of order n size. Order n means n, n minus 1, n plus 1, something like that, very close to n. Suppose you take something like this. They are both of n size. I'm adding something here, 25. They are both of n size. How much time will you take to combine them? Hmm. Acha. You said in response to that one. I thought differently. Uh, so the question is, suppose we have two sorted arrays and we need to combine it so that the final array is sorted. The final array of 2n elements is sorted. How much time will I take to combine them? If we do selection sort, that suppose I add it and then I'll do selection sort, how much time will it take? Order 2n square, where we can say that is equal to order n square. What I said is that I'll just join them and then I'll sort the entire array. I'll take order n square. Can we do better? Yes. Thank you. So I took n in both. So yes, if it is n and m, then order n plus m. Why? Because we can just check from here. Follow this. 2 into n, yeah, 2 into n, right? Precisely, it's n plus m or 2 into n, however you say. First, we will check that who can be the first element of this sorted array. Which element can be the first element? Definitely either the first element of the first array or the first element of the second array. Can it be from here? Now again the question arises, which I was referring to in the restaurants part, that in order to find the first candidate, over here you don't need to explore everything. You just need to explore two elements. The first one of this one and the first one of that one. So you just need to analyze these two and say which is the smaller one. You know that one is smaller. So what will you say? I place 1 and I can shift this pointer to 7. For the next blank, I need to consider only 7 and 2, and I will see that 2 is smaller, so I'll write 2 and I'll shift this pointer to the next one. Now I'll compare only 3 and 7. I'll say only 3. Now 3 will come. So that is how we are proceeding. So every moment we are just comparing two elements. Just a moment. Every moment we are just considering two elements, and how many times are we considering this? The number of blanks which we have to fill. That's it. That is the total thing which we are considering, the number of blanks we have to fill. What is the total number of blanks? 2n. So can we say that for all the elements except the last element, let us leave that for the moment, for 2n elements we'll compare at most 2 elements? Can we say this? So this is the total number of elements which we are considering at every step. Can we say the total number of operations is thus order n? Because every time we are just considering two elements. When we have considered it, from whichever array we have considered it, we are pushing the pointer forward. And then we are doing the future comparisons. Does this make sense? That this merge operation will be order n. Does this make sense? Cool. Great. So I hope it is clear to most of you. We are just using greedy approach over here. So greedy, that will come later on. We are just using greedy approach over here. So when it comes over here now, what can we say? That okay, when we have to sort the array of length n, what can we say? That sort the array of length n by 2, sort the array of length n by 2, and after that I require exactly n comparisons, n kind of n different steps, or basically n minus 1. N minus 1 is the number of positions. So I can tell n minus 1 is the number of positions where I have to compare. So these many times I have to compare two elements. So I can tell n minus 1 is the computation over here, plus this time plus this time. So can we say that Tn, the time taken for n elements, this is exactly equal to T of n by 2, which is for the left half, plus T of n by 2, which is for the right half, plus n minus 1. Can we say this? So these two, this is for the right half, and this is the self work that our function is doing by taking both the components. Now what can we check from here? We can thus say that T of n is equal to 2 into T of n by 2 plus 1 plus n minus 1. We can for a moment say that this is less than equal to 2 into T of n by 2 plus n. How can we say this? We can, write this T of n by 2 in a similar manner. We can break it into n by 4 and those things. So can we write this in this manner? 2 of 2 into T of n by 4 plus, here what is the value of n when we are exploring T of n by 2? T of n by 2 will look something like this: 2 into T of n by 4 plus n by 2, or basically this is the kind of thing. So n by 2 is going to come, so we are going to write there, in that step we are going to write n by 2 inside the brackets plus n. So what happens when we come out, we will see this is 4 into T of n by 4 plus n plus n, which is 2n. Can we say that this is 4? We can also say that in the next step we'll be getting something like 8t n by 8 plus 4n. I'm sorry, 3n. How? If you do this, if you expand it, you will get this. How it will come? 4 into, within bracket this thing will come, this will be n by 4. So 4 into n by 4 will again bring an extra term n will get added with 2n and it will bring 3n, and inside the 4 will get multiplied by 2, and over here you will get 8. So what are we doing? We are breaking n continuously. Yes, right. So we need extra space. We are coming to all of those things. We are continuously breaking it till we can reach to the very finer gradients, finer granular elements, which are 1. The area of one element, we know how to do it. T of 1, that will take constant time to sort. We know that is 1. How much time will it take to reach 1? At some point of time, we will see that this will come to, you can understand from here. What we are getting basically is something like this. At any ith step, you will have 2 to the power I into T of n by 2 to the power I plus I into n. Can you see that I equals to 3 is holding for this, I equals to 2 is holding for this, I equals to 1 is holding for this. So this is basically following this kind of a pattern. Oh, I think I can recognize you. Yeah. Hi, bhaiya. After a long time. So that is basically the story. Yeah. So when we reach this stage, what we are having, where will we end it finally? Finally, we'll be ending it at a stage where it will be reaching T of 1. After that, we don't have to proceed further. And when shall it be reaching T of 1? When n by 2 to the power I will be equal to 1. And when will it be equal to 1? When I will reach log n, log of n to the base 2. That is basically where we can find that 2 to the power, again log 2n, which we can safely write as n into T of 1 plus I we can replace by log 2n, so it is log 2n, and over here also n. And over here we say that T of 1 is equal to 1, so we can write that this is equal to n log 2n. This is basically how we are arriving at the time complexity. What I wrote here is the time taken to sort n elements. And the time taken to sort elements, n elements, the way I'm deriving it is I'm not just breaking into two parts and leaving it. For both of those parts, I am asking it to do the same thing for their own selves till they reach this particular stage, T of 1. So if we look at the recursion tree for 16, then for n equal to 16, if there are 16 elements, then it will break into parts of 8, it will break into parts of 4, this will break into parts of 2, and over here as well, and 16 ones at the bottom layer. And that is how we'll be getting this entire thing. Try to understand that at every step what we are getting is n operations are taking place. And why every step n operations? because in the first step there is n operations taken to merge. In this step, again the merging operation is n by 2 over here and n by 2 over here, if we consider n equal to 16. So this is why the total is always n, or it is bounded by n. We can say that, oh, okay, over here it is n by 2 minus 1, there it is n by 2 minus 1. Summing it up somewhere, we will get the same thing. That will be less than equal to n. So when we just add the operations over all the levels, we will get n log n time complexity. That is basically what, if we use two pointers, we can do it in order n. Okay, I think this was in response to some other problem, some question being asked. How n minus 1, n minus 1 which step? N minus 1, is it the first step? So after the two fragments give me the sorted lists of size n by 2 each, what I need to do is, now I have the n elements, I have to place it in the n correct positions. So for the first n minus 1 positions, I need to check with 2 elements each. So for all of these, you can even place 2 and you can form your own recurrence relation. That will not bring a major change. 2 will get multiplied in all the parts and ultimately 2 will vanish. So the important part is that we have to compare, every time we have to compare two elements for the first n minus 1 positions. If you have to add two lists of, suppose, this size of 8, then for the first 15 elements you need to compare. For the last element you don't need to compare. You have only one element left. So that's it. Can we perform better than log n log n? No, we can't do it. But yes, if the elements fall in a certain range and the range is smaller than the size of n, then we can definitely use counting sort, that is a non-comparison based sorting. We can do better than n log n. So yes, precisely the answer is yes. Count sort. Yeah. So a question that I would like to ask you all is, why only two elements? Can't we use more than two elements? Sorry, more than two partitions? Can't we partition an array into three parts and then take that and merge it and do it? What will happen then? Won't that be good? So instead of two partitions, instead of doing it in a binary manner, if we rather proceed for a ternary fashion, that is, we'll be dividing every array into three parts and then we'll be combining it. So this will look something like this. If we have something like 27 elements, it will divide into parts of 9. It will divide, every 9 elements will be divided into parts of 3, and over here as well. And 3, this will also be divided into parts of 1. And similar for all of these. Let's see. Let's see, we have the same recurrence relation. Comparison part will increase. Comparison can increase. It will take same time. Good. Thank you. Good responses. So if we see Tn, this is basically what we get. Every subpart will be of time, will take time t of n by 3. And there are 3 such parts, right? From every part, we have 3 such parts. Now what we need to do? This is a ternary way of doing this merge sort. Now what shall we do? For combining them, we again have n positions. And for the first n minus 1 positions, 1, 2, n minus 1 positions, we are concerned about selecting elements. Now you have 3 elements. You have A, B, C. How many comparisons do you need to find out the least element? How many comparisons do you need to find out the least element out of 3 elements? Do you understand where A, B, C are coming from? Suppose we have these 3 sorted arrays, and over here your current pointer is pointing, over here your current pointer is pointing, over here your current pointer is pointing. You need to find the minimum out of these 3 elements. So there are 2 comparisons, right? So by comparing A and B, you find out the minimum. By comparing that minimum with C, you find out the minimum out of all the 3. So there are 2. So when you place 2 over here and the total number is n minus 1, let's write it n for the time being. Similarly, as we wrote the previous one, so we can write less than equal over here. And if we continue this is less than equal to 3 square t of n by 3 square plus 2 into 2. This should be 2 into 2, that is 2 into 2n. Every step it will take 2n. It will end up somewhere over here, 3 to the power I into t to the t of n by 3 to the power I plus 2in or I into 2n. What will this result in? This is, we know this is 1. This will, okay, so when it will become 1, 2 into 2i into n, right? So when this will become 1, you will have n over here, you will have t of 1 over here, you will have 2 into I into n over here, which is the height of this. What is the height? Now the height is smaller. You have log of n to the base 3. We have optimized the height. But let's look at this thing. This is the term now. And over there you had n log 2n. Right. So here we have 2n log 3n. There you had n log 2n. When you sit and compare them, what do you get? This one we can write it, this is elementary mathematics, or maybe plus 12, like class 12 mathematics. You have 2 by log e3, or maybe log 10 3, and over here n log 10 n, and over here log which we had previously, we have 1 divided by log 10 2, and here log 10 n, n log 10 n. This part is the same, this part is the same, so it is not important to us. Which is greater, this one or that one? You can find out that this one is smaller, this one will be smaller. Don't remember the values, it were 0.301, right? It was 2 by 0.301 maybe, and this was 1 by 0.477, right? You can check it. Log of 3, it is 0.477, and log 2 you have 0.301. So that's it. What do you get over here? This is basically giving you a larger value, and this is giving you a smaller value. That's it. So if you check this, this will be a smaller value. That means this is the merge sort which we did previously, where we had logarithm to the base 2. We are winning in that case fractionally. So that is why we don't increase the number of parts. We just limit it to 2 parts, because fractionally it performs better than the ternary case. Even when you compare binary search and ternary search, it is the same thing, right, Utkarsh? So it is binary is always better. That's it. That's basically divide and conquer. That's basically how divide and conquer is done. The important thing that I want you all to remember is, what divide and conquer does is, it breaks a problem into sub problems and solves it by combining them. But in contrast to dynamic programming, which is a very related subject, you have slightly different elements. Over there you need to find the relation, you need to find the overlap between sub problems, and you need to frame your sub problems in such a manner that they overlap and reduces your computation time. Over here the problems don't overlap. If some of you know dynamic programming, you all can relate. These two problems are not overlapping, these two sub problems, they are completely independent. This part solves independently, this part solves independently, this part combines them. That's how you get it. Okay, and it happens at all the levels. You solve parts and you form it. But this was, in the first time when you think it, it is quite counterintuitive. You are doing the same operation on smaller pieces. How can you improve? We are doing deep. Okay. Yeah, thanks Vaishnavi for the compliment. So yeah, so what we are doing is, we are doing a simple thing. We are saying that just divide it, a kind of recursion kind of thing, which you did yesterday, I think. So we are just doing the same operation. If we do simple sorting over it, now we are not doing sorting at all. We are saying we have two sorted lists, we'll just be combining, and every step we are just doing that same thing. We are not sorting at any stage. We are not doing selection sort or comparison or finding, swapping or anything. Just one single combine operation at every step. So that is divide and conquer. Divide it, conquer it, combine it. Like, that's basically how it works. Fine. I think we'll look at another problem which has been mentioned by one of you. I slightly mention it. Count the number of inversions. Count the number of inversions in an array. How can we do it? Inversions in an array. This means that you have to find the number of ij pairs in the array such that I is less than j and ARR I is greater than ARR j. How many such possibilities do exist? How many number of such pairs do exist? So what is a brute force? Once again, we will look into all the pairs and we will find out. That is a brute force. What is a different way of doing it? We can say that suppose this is our array. From here, from this part, from this left part, it sends us n1. That is, n1 is the number of inversions inside myself. This subarray says, now what are the three different kinds of situations? First is the inversion occurs over here, that is inside the subarray. Both I and j are present inside this subarray. Another is it is totally present inside this subarray, or it is present maybe something like this. I is present over here, j is present over here, and you find that ARI is greater than ARJ. So what can you say? It will return n1 considering all these I things that are existing. It will return n2 for all these I things that are existing. And when it will combine, we just need to take into consideration these extra things. Right? So now, after it has got sorted, what can we say? That here ARR I is greater than j, ARR j. So we can say that all these elements, after this, all these elements will be even greater than this ith element. I plus 1, like whatever are present over here, they will all be greater than this ith element. And hence, because we know that ARI is greater than ARJ, what can we say? Whatever k will occur over here in this range, for all of them ARK will be greater than ARJ. Can we say this? And just by using this idea, we can say now we don't need to compare them. We can just focus on something else. That is how we do it. So we say that, okay, for jth element, we have seen for jth element, this range is giving us all the elements, all the inversions with this jth element, I, j, I plus 1, j, I plus 2, j, whatever. Okay, so suppose I have these two arrays. Now let's take the previous example we had. Okay, let's create another example. We have these two parts, these two sub arrays, 1, 3, 11, 16, 2, 4, 10, 11, or suppose we take 19. Isn't there going to be a quiz today? Well, I don't know. So anyway, let us see if we can cover if we can close it well. So for this first element, when I compare it with the first element over here, 1 when we compare with 2, what can we say? That 1 is less than 2, so this is unimportant to me. Let us focus on 4 now. So 2 cannot, okay, we'll have the quiz after this, right? So what can we say over here is that 3 is the first element which is having an inversion with 2. Can we say that after 3, whatever are occurring, they will also have inversion with 2? Because 3 is greater than 2, so I can say this is a sorted array, so 11 and 16 will also be greater than 2. So we can say that they also form an inversion with 2. Similarly, we can say that the moment we find that 16 is creating an inversion, or maybe 11 is creating an inversion with 10, we can say, okay, now 11 and 16 all will form an inversion with 10. With 10, I don't need to say anything. So when this inversion is occurring, I will just tell move ahead. We can directly say this. One another thing is that if 11 has inversion with this 10, can we say 11 will have inversion with these elements as well? So basically, if for each such element, if for this 11 we find out which is the last element with which it has an inversion, we can find out that 11 will have inversion over all the elements that come up to there. So that is basically what we are doing over here. Yeah. Yeah. So what we are doing over here is we are utilizing this, knowledge of sortedness. We know because it is sorted, and I know that 11, it last forms an inversion with 10. I can proceed this j up to where it will actually keep on facing inversion, and then I'll say that this j and this I, this faces an inversion. So I will form an inversion with all these elements. Now there are many rectangles over here. So I will form an inversion with all these elements. It will be greater than all these elements, and all the elements in front of I will be greater than all these elements as well. So we can directly, find out a formulation for finding out the number of inversions. Does that click? Does that ring the bell? Yeah. Okay. So that is basically what we are doing. How will be again moving I and j? We need to think on those steps, and it will be a good practice if you do that on your own. But the important thing is you should not come back. What I said is, if you move I forward, you should not again come back. If you should not bring I backwards. If you move time and again, then the complexity will increase. If you always move in the forward direction, either I or j, then the time complexity will remain fixed at order n. So you now understand that if these two arrays return the n1 and n2, which is inside them, and you find out the relation, the relative, interactions from those, if you find out the inversions in order n time, so it is again bringing the same kind of a relation, that you need to depend on how much time your sub problems are taking, plus again order n is needed. So n, suppose we take it like this, so it is again the same complexity analysis, order n log n. Base of a logarithm does not matter in asymptotic time analysis. So that's it. That is about divide and conquer, and we have done one problem, which is counting the number of inversions. I would definitely encourage you to do quick sort. um, that is a slightly more non-trivial algorithm in the sense of the time complexity analysis. We know that the maximum is n square, but again the randomized time complexity analysis will give n log n. So definitely do it after this. Spend some time in that. I think we can look at one or two greedy stuff, and then we can close for today. Hope you are enjoying it. So in divide and conquer, do this single thing: form your sub problems, call them, perform them independently, and then combine them. That is basically divide and conquer. Break into sub problems, solve the sub problems, and combine them. Then we need to divide the array only once for getting two arrays, or keep on dividing till, yeah, keep on dividing till we get one element. Of course, if you divide once, how will you be able to do it? So yeah, divide it and then okay, thanks. So divide it and keep on dividing, then only you can get this time complexity analysis. Else what will happen? Else over here again that n square will be consumed, n by 2 whole square and those things, plus n. So yeah. Okay. So let's do some, let me see what will be a nice problem to close. Hmm. Okay. uh, okay, thank you. Suppose suppose we have n jobs, and we have one machine to perform all the jobs. There are n jobs, there is one machine to perform all the jobs, and every job is associated with a running time. So there is a1, a2, a3, and so on, which dictate what are the running times up to an. Now the completion time is, suppose you arrange them in some manner, then the completion time will be the time that this job takes to complete plus the time that the previous jobs have taken to complete. The important things are only one job. Now this problem that I mentioned, this is called job scheduling problem, which is a very advanced level problem. Basically its variants are very advanced. If you change the number of machines, if you change the completion times of machines, if you change the performance times of machines, if you change the multi-threading capabilities of machines, it will expand. The problem will expand till it reaches the NP completeness. If you know the NP completeness, that those are problems which cannot be solved in polynomial time. So we will be only considering one variant, which is there is one machine, only one job runs at a time on that machine, and lastly completion time equals to when that let us represent this by ci equals to time when it ends. Yes, I'll come to it, Rohan. I'll come to it in this particular problem, and with that we will close. How can we understand that it has to be solved by greedy? This is the question that I want you to ask yourself every time when you solve a problem by greedy, because 99.99% of the problems can be solved by greedy very easily, but only 0.01% can be proved. I'm talking about the general attitude of problem solvers. The moment a problem is solved, there is very less propensity to linger for a while and check about whether the greedy will work or not. But this habit should always exist, that you should always be perfect about why the greedy works. So we'll look at that. Completion time ci is time when it stops. Time when it stops minus the initial time, which is 0. So suppose I give you three problems, 3, 1, and 2. Suppose I give you these three jobs, and I say you that you have to run in this order only. How will it run? The first one, it will take 3 seconds to complete. The second one, how much time will it take to complete? From the very beginning of the process, it will wait for this job to finish. So 3 seconds it will wait. Then it will use 1 second to process itself. So it will have 4 over here. And then when this last job will come, it has to wait for up to these 4 seconds. And then it has to process for 2 seconds. So we have 6. So this is basically our total completion time. This is the total completion time of the last job. Now if we focus on what is the sum of completion times of each job, suppose it is something like that, that if the job completes after t seconds, then we will get n minus or suppose something c minus p rupees. So whatever delay will be caused for particular job, that many penalty has to be paid. So I am concerned with minimizing this entire set of t's, this entire set of all these t's. So what will be the sum? The summation is 3 plus 4 plus 6, which is 13. What is this 13? Time taken for the first job to complete is 3. Time taken to complete the second job is 4. That is, time taken when the second job completes is 4, and time taken for the last job to complete is 6. And now I'm blindly adding them up. This is 13. But when we look at a different iteration, suppose 2, 3, 1, then what is the total time taken? For 2, the time was 6. So we will have, okay, sorry, 2 is the computation time. So it will take 2 seconds. 3 will wait for this 2 seconds, then 2 plus 3 will be 5. Then 1 will wait for 5 seconds, and then 1 plus 5 will be 6. What is the summation? So what is the total sum of the completion times? It is 13. Is it really making sense? 7, 2, 3, 1. Fine. Let us look at another possibility, which is 1 to 3. 1 to 3, if we look at this, first one will take 1 second, second one will take 3 seconds, and the last one will take 6 seconds. So yeah, thank God. We have got something better. So yeah, so 256, this is see these two particular arrangements. If we solve the jobs in this manner, we are getting a total completion time of 13 seconds. How we are solving it? Basically, we are saying that this is the timeline. This is your t equal to 0. For 3 seconds, one job is going to run. I'm sorry. For 3 seconds, the first job is going to run. For 1 second, the next job is going to run. And for 2 seconds, the next job is going to run. And over here, we are going to say in a different manner. We will say that instead of 3, 4, 6 being these are completion times. These are the completion times for these jobs. In the next example, in this last example, it will look like this. Over here we'll have 1, over here we'll have 3 because this one takes 2, and over here we have 3, so this has 6. So yes, we have to consider the waiting time. So everything taken together, this is leading to a better total time. And I want you all to optimize this total time. So this rearrangement, if we rearrange the jobs in some manner, then this total time can change. How can we rearrange, or what can be the minimum total time given that there are n jobs and all have their waiting times? How can we find the minimum time? How can we find the minimum time? This is where we apply greedy. What we can say is that this delay, exactly, shortest job first. So this delay, what this is doing is this is creating the overhead for the next job. So in operating systems, you will study many different complex kinds of scheduling. Somewhere priorities are used, somewhere round robin is prioritized, and many different paradigms are there. But see, if we just, this is just an objective function. Later on, when you study those algorithms in your operating systems, try to understand what the different objective functions are. Because if the objective function is only the total sum of the completion times, then always there is one simple approach that is going to work. It only depends on what your objective is. If your objective is that you have to please a certain person first and you have to process his jobs before everything, then that has to be handled separately. But always it depends on what priority you're using. Exactly. Scheduling in OS, shortest job first. So now here you come, you have this in shortest job first. What you do is you will just sort the array in terms of the computation time. Whichever has the lowest computation time, you will bring that before. So you can always say that if we arrange the elements such that we will have the new computation times in this order: b1 less than equal to b2 less than equal to b3, and so on up to bn, where b1 refers to the computation time of the newly declared first job, and bi refers to the computation time of the ith job in the rearranged order. If you do that, then this is going to give us the best one. How can we prove it? This has worked in this case. It has given us the better answer than these two. How can we prove it for the other algorithms? Sorry, for other instances of the problem. An instance of a problem is where we take an example of a problem and we assign certain values to it. That is when we call that an instance of a problem. So a problem means basically job scheduling is a problem. But when we say n instances, a1, a2, a3, and those things, that is an instance of a problem. Greedy algorithm should be declared as the correct algorithm, or SJF, if it works for all instances of a problem. So it should be generically proven. For that reason, let us take that greedy algorithm. Just a second. Yeah. So greedy algorithm is going to consume some something called sum. This is going to be the final answer. And suppose somebody tells us that the optimal answer is going to be sum star some star, and it is going to have some set of instances, c1, c2, something like that, up to cn. And over here we have b1, b2 up to bn, right? This is what we'll be doing. This is basically how it is proven, and this particular form of proving is called, what I'm going to show now is exchange arguments. Theoretically, this is what it is known as, exchange arguments. That how can we prove that greedy will perform as good as the optimal? It is not necessary. Suppose you have something like this, a1, a2, a3, suppose all have the same times, all take 1 second, then you can rearrange in any manner. The jobs can be rearranged in any manner, so it is not required that the order has to be exactly the same, but you can have different orders. What you need to prove is greedy should do at least as good as the optimal. If you can prove that, then you have proven that greedy is always optimal. How can you prove it? Suppose for this we will say that fetch the prefix longest prefix common in both arrays, b1 to bn as well as c1 to cn. We'll fetch the longest prefix which is common in them. So suppose the longest prefix is some I, or suppose it is what can we call it, suppose I minus 1. I minus 1 is the last job which is matching this order. The next job differs. Here we have something and here we have something else. So basically I'm telling that bi equals to, sorry, bi is not equal to ci, and before I, all the bi is equal to bj is equal to cj for all j which is less than I. I'm telling this. So this is how I am first of all finding out that suppose there is a difference in the scheduling. How can we analyze it? Now up to here it is matching. Let's say we have bi over here, we have ci over here. This is the optimal. So suppose this is cj, okay, and this cj matches this bi. Why will this cj always be in front? Because up to here everything has matched. So it is out of the picture. Now bi, suppose it is not equal to ci, so we can say that bi is equal to cj for certain j which is after I. Cj is not matching, and when we find that, what we will say is, now swap the answer, and I need to know what is the new solution, what is the new sum. So here suppose you have sum star, I need to know what is sum 2 star. And when I find sum 2 star, what I'll be doing is I'll just be swapping these two elements. So I'll just be swapping these two elements, this element and this element. So what will be the sum? Let us consider the sum up to here will be the same. So let us consider here in terms of sum star, which is the initial sum, up to I minus 1, it will be exactly the same, plus it will take the additional sum. Now cj, it will take this cj, which is basically bi will come over here, bi plus this particular sum, let us treat it as s, okay. So bi plus s is this sum, plus the number of elements that come over here. For that number of elements that come over here, for that, what is the waiting period? Waiting period, we can say it will always be the waiting period up to here plus that completion time. So for all these j which will lie in I plus 1 to okay, I should use a different variable. From I plus 1, that is just after this I, up to j, I will check how much it has been asked to wait, some waiting time plus its own completion time. So this waiting time is also specific to k plus its own completion time. And what is the completion time? A c of k. That is it. Now this wk will be different from what we had in case of sum star. What is sum star? When ci was here, when cj comes over here, this will be slightly different. Now after this we will have this cj term. Up to here you can understand we are only swapping this. So cj will complete at the, like when ci comes here, it will complete at the exact time. Why? Because the summation will be same. So it will take, like, the final job, if you consider any interval, then the final job will take the same amount of time to complete. The final job will complete because they are not waiting in between. What I mean is, if you see this, all these examples, the final job is always taking 6 seconds to complete. Why? Because that is equal to the sum of computation times from the start of the array to the that position of the array. So we can always say this particular part is going to remain exactly the same, which is exactly equal to sum star of j to n minus 1. This is going to remain exactly the same. So I am forming sum 2 star. What is this representing? That after swapping, what will be the sum? And I am defining that in terms of the previous sum. So what I'm getting is, this part will be the same. This part will be the same. So up to I minus 1, it is the same. Up to j onwards, it is the same. Over here, bi plus s. Instead of ci, we just have bi. S is basically this sum. This particular sum is s. So we know instead of ci, we have bi. Now, how had we chosen bi? How had our algorithm chosen bi? This bi is our algorithm, greedy algorithm, and this is, we are taking the optimal choice, the optimal schedule. How had we chosen this? We had taken the shortest job in front of us. So among these remaining ones, we have taken the shortest job which was ahead of us. So bi is definitely going to be less than equal to ci. We can definitely say this. That is why we have chosen it. So this part is always going to be lesser or equal. bi plus s is going to be lesser or equal compared to ci plus s. So from sum star j, we have improved in this part. First part we are in the same position, last part we are in the same position, this part we have improved. Look over here in this middle part. What are we doing? Over here we have a less expensive item. Instead of ci, we are having cj. Cj is basically bi. So what we basically had is, over here we had ci up to here. Ci was completing over here. Instead of that, we had cj is completing over here, and then we have the same kind of jobs. Whatever we had over here, we have the same kind of jobs. So their completion times is definitely going to be lesser. Over here, this completion time t dash is going to be lesser than this t double dash. This one is going to be lesser than this, and so on. So all these are going to be lesser than equal the previous ones, whatever we had in sum star. So this is what we had before, previous, that is our optimal. And here what we are telling is, in optimal, we'll just do one swap and we will see this has happened. What we will see as a result, that here we are improving, here we are improving. So this means that sum 2 star, you can analyze this later on as well. This is always, you have the recording with you, I would encourage you to analyze it. Okay, but you should do it by yourself, then it will become very easy. It is actually lesser than equal to sum star, always. You can understand it. But the interesting thing what you have done is, suppose, let us assume that yeah, because sum star we know that is the optimal, it cannot be greater, it has to be equal. Why? Because optimal, somebody has told us, means it is optimal. We have to show that greedy is also optimal, so we know that it cannot be lesser, it has to be equal. That fear we had is greedy should not be greater. If it is greater, then it is a bad algorithm. But from here we see that it has to be lesser than or equal to. So how we did this? By exchanging one algorithm. And as a result of exchanging, what did we find? That when we exchanged, we have, instead of ci, we have cj over here. And when we have cj, that means now with our greedy algorithm, in the ith position also the jobs are matching. cj has come over here. our performance has not improved. Our performance might have improved, but it has not decreased, it has not you know deteriorated. But what I can see is I have a longer prefix. So what I was seeing over here, that I'll fetch the longest prefix, and then I'll be finding this I'll be changing it, and then I'm doing this operation swapping. As a result, what I'm getting, sum to star is corresponding to a particular arrangement which has even a longer prefix. And hence, if I do this exchanging again and again, what will I eventually land up to? I'll eventually change my optimum value, to slightly varying things. I know that I've changed it to star, or maybe we can call it opt2. Why we are calling it opt2? Because the summation is equal, the cost is equal. So we have changed it to opt2, and what is happening, this is having a greater prefix with respect to our greedy algorithm. And hence, as we go on doing this, what will happen, the size of the prefix is going to increase till we complete it, till the entire thing matches. And hence we say that at the end we will eventually reach the greedy one. Why? Because we'll reach something which will have the longest prefix possible with this greedy, so that no such I will exist. Because if such I exists, we can find out another counterpart which will be better in the sense that either it will be optimal or it will be same in terms of the performance, but the I will be greater. How long can I go? I can go from 0 to maximum n minus 1. It cannot cross that. N minus 1 means the last element. And as a result, what will happen? The longest prefix is always the total thing. So basically, why greedy works is because greedy performs something called local optimum. Greedy does something called local optimum. And if we can say that this local optimum leads to a global optimum. Why global optimum? Because now I'm not concerned about only the local things. I'm considered about, out of all possibilities, which is the best. If greedy helps in finding that, then we are done. So over here, what I'm doing is, this is a local change. I have done one argument change. So there's a local change. And when we do totally up to this, we say that we have seen all possibilities. So over here, we are basically optimizing it totally. We are considering it globally. So in case of greedy algorithms, definitely we could have seen many other problems. The idea is always to proceed in that manner. The shortest one first, longest one first, um, least one first, and those things, whatever variations you have. You have some problem which is, you have to schedule some events. Every event has got an arrival time and a closing time. So over there, you schedule the events such that you need to maximize the total number of events you can have. So over there, we suggest that sort them according to the least, like in the ascending order of finishing time, and go on taking if you can take it. That is how we do it. If you look at very advanced, round robin is slightly different. Round robin, there the objective function is totally different, because round robin, in operating systems you'll have it, there is something called the response time. So something requires the user to feel that that can remain live, the application is always live. So there we always prefer round robin, so that the user feels okay, from 1% to 2% it has progressed. The user doesn't care about how much time it will take to reach 100%, but the local thing is important. So all the processes, when they increase by 1%, that is basically what round robin actually helps in doing. So the problem that I was telling is, if we have arrival time and closing time of every job, and we have to schedule the jobs in such a manner that we can have the maximum jobs such that no two jobs clash, then we order by the finishing times. We don't order by the arrival times. Anyway, that can be like, yeah, we order by the finishing times, and again the proof will go something like this. So whenever you approach such problems, Don't fly away just at the thought that it is again that complicated thing which had been explained on that session on 6th of June in red colors. Don't get intimidated by that. Just proceed it congenially, smoothly, and if you have the interest, try proving it. What I've done here is no complex mathematics. It is simply what will happen if I do make this change. You also, I'll encourage to do the same thing. All right, that's it. I hope that you have been able to learn something, everyone who have been present in this session, and it has been a bit didactic, or at least interesting to all of you. So fine. Any queries, any questions? Last 1-2 minutes. We can have that maybe. Okay. Some tips for placements. That's a long thing. Placement is a there are so many topics, but for placements, this is one thing that I would suggest. The way I approached a topic, bear this spirit in mind, that when you are approaching a topic, approach right from scratch. Don't assume that the interviewer will assume certain things for me. If you say these are the things, this is why it works, and when you also study in that manner. There are only two things that matter in placements. One is whether you have the fundamentals, you can solve the questions, or and the second one is whether how your attitude is. So if you can, you have a command on these two things, the performance and the attitude, then you are done. That's it. Okay. Thank you.
Thank you, sir. I would like to thank Saptashi sir for making our learning easy with your experience. Thank you for inspiration, for encouragement, for being here, and most importantly, for giving your time and making presence. And thank you, everyone. You are a wonderful audience.
Yeah,
Now, I
thanks
would
from my
like to
end as
announce.
well. Yeah, thanks from my end as well, and the pleasure is mine. Thanks for having me over here, and thanks to the audience. It has been quite interesting and
Thank you,
spirited.
sir.
Good.
Now, I would like to announce yesterday's quiz winner. The winner of yesterday's quiz is Amit Singh from ABES Engineering College. And you can be the next winner by solving today's quiz at very first. All the best, guys. Link had been uploaded in the chat box. The quiz will be at PropBytes platform, and the winner will receive T-shirt from PropBytes.
Okay. Bye. Thank you. Bye.